Today we're going to be discussing the chi-squared test. We now turn to our last hypothesis test. The chi-squared test uses categorical data that are usually given in two-way tables. The entries in the tables are counts. So we're counting something that has a certain characteristic. For example, different dog breeds, number of students with left or right-handed, male or female, students who took the SAT. Those are what counts are. You're counting individual things. There are three chi-square tests: goodness of fit test, test for independence, and test for homogeneity. The chi-squared distribution is asymmetric and does not have any area to the left of 0. So you have to look at the test statistic. The distribution is determined by the degrees of freedom and becomes more and more normal looking as degrees of freedom increase. So as we're looking at our chi-squared distribution, so if I only have 2 degrees of freedom, my chi-squared distribution would look something like this. And that's with degrees of freedom equaling 2. If I increase my degrees of freedom to something around like 5, it'll look more like this. And if I were to increase it even more, my degrees of freedom to say like 10, it would become more normal looking. Note that the chi-squared test statistic measures the discrepancy between your observed counts, which are your data, and your expected counts, what the null hypothesis assumes to be true. And this is what we've been doing since we started. All three chi-squared tests use the same test statistic. The formula is on your formula sheet. Also, the chi-squared test statistic is the sum of the observed minus expected values squared all over the expected values. Let's look at the first one, the chi-squared goodness of fit test. How well do observed values from your sample fit an expected model? So first we have our null hypothesis. Distribution in sample matches the hypothesized population distribution, and you need to have that within context. Your alternative hypothesis is the distribution in sample does not match the hypothesized population distribution, which also needs to be within context. Your conditions are observed cell counts are based on a random sample, so you have to state that within context, and all expected counts are greater than or equal to 5, which tells you have a large enough sample. Your degrees of freedom are k minus 1, where k equals the number of rows or the number of columns. And your expected counts are the hypothesized percentage times the number in your sample, n. The matrix will either be a row matrix or a column matrix. It's a 1 by, so you just have 1 row or 1 column. This is your clue to a goodness of fit test. If it's just 1 row or 1 column, it's a goodness of fit test. Some calculators have a goodness of fit test on the calculator. If not, these are easy to do by hand. Those of you who don't have a calculator that has it, we can go over in class how to do it by hand, but we're going to use the calculator for this example. Let's look at the goodness of fit test example. As the manager of a small gift shop at a mountaintop ski lodge, you're in charge of ordering the stock that will be sold during the year. Since this is a ski area, you know that you will need to order a great deal of flavored cough drops. In order to find out which flavors sell best, you contact the manufacturer of Cool Cough cough drops. The manufacturer tells you that the customers prefer different flavors in the following proportions, listed in the table. Since your favorite flavor is lemon, you can't believe that this distribution is correct. In order to check the manufacturer's claim, you decide to conduct your own simple random survey of the flavor preference of 50 skiers. And your results are in the table below. Conduct a chi-square test to assess the goodness of fit of your survey data to the manufacturer's distribution. In addition to showing your work, list the chi-square statistic and the p-value. Then write a sentence or two explaining your conclusion. So we're going to go ahead and do this here. So this is our example for goodness of fit, cough drop flavors. So I'm going to title that up here. So this is our chi-squared goodness of fit test. And we're going to do this at a significance level of 0.05, since 1 was not given to us. Our null hypothesis, we have to list first, is flavor preference distribution in sample matches manufacturer's stated distribution. Our alternative hypothesis would be flavor preference distribution in sample does not match manufacturer's stated distribution. And our conditions, it does say it's a random sample of 50 skiers. However, we need to see if all expected counts are greater than or equal to 5 to give us a large enough sample. So you're going to go back to your data and you're going to go ahead and do this here. So what we have is this table here. This is our survey results. Okay. So our actual survey results are going to be our observed values. Our expected counts are going to be in parentheses, and you need to show this. You need to write it here, and you actually need to write them in parentheses next to them. Okay, so to find our expected, since we have 50 skiers, to find our expected for cherry it would be 50 times 0.35 because it's 35% for the distribution, and that would be 17.5. So we'd put in parentheses 17.5. So you do the same thing for Coolmint. It would be 50 times 0.2, which would be 10. So we would have 10 here. So on and so forth. We know this would be 10 as well. 15% of 50 would be 7.5. And 10% of 50 would be 5. So you do need to show this. And I look at all these values. They are greater than or equal to 5. So we would state all expected counts are greater than or equal to 5. So we have a large enough sample. So now we need to actually show how to find the chi-squared statistic. And your chi-squared statistic from that formula that we wrote is the sum of all my observed minus my expected squared all over expected. So if I just went right through, my observed was 15 minus my expected for the first one for cherry, 17.5 squared all over 17.5. Plus, now you would go ahead and do Cool Mint. Cool Mint would be 9 minus 10 squared all over 10. Plus, next would be Eucalyptus, which would be 12 minus 10 squared all over 10. Plus lemon, which would be 12 minus 7.5 squared all over 7.5. Plus menthol, which would be 2 minus 5 squared all over 5. This equals 5.357. And my degrees of freedom here is 5 minus 1, which equals 4. So you can go ahead and put this in your calculator. You have the chi-squared GOT, goodness of fit test under test. And we would get a p-value of 0.253. So my p-value is greater than alpha because 0.253 is greater than 0.05. So we would fail to reject the null hypothesis. Not enough evidence to suggest. Flavor preference distribution in sample differs from manufacturer's stated distribution. And that is your chi-squared goodness of fit test. The next one is the chi-squared test of independence. Is there an association between two categorical variables in one population? So here your null hypothesis would be there's no association between two variables. The two variables are independent, and you need to state that within context. The second would be the alternative hypothesis, there is an association between two variables, and the two variables are not independent, and you also need to state that within context. Your conditions are observed cell counts are based on a random sample. And again, all expected cell counts are greater than or equal to 5 to have a large enough sample. Degrees of freedom are the number of rows minus 1 times the number of columns minus 1. And your expected counts are the row marginal total times the column marginal total over the grand total. And your matrix will be 2 by 2 or larger. And the calculator will run the test for you. So this is your chi-squared test of independence, which is in your calculator. Let's look at our example for this. The Super Vending Machine Company, SVMC, plans to install software vending machines in middle schools and high schools in Montgomery County. The SVMC market analysts wish to know whether flavor preference and school level are independent. A random sample of 200 students was taken. The distribution of the school level and soda preference for the sample are given in the table below. Does this data indicate independence at a 0.01 level of significance? So we're going to go ahead and have this example. So you would first, again, state the name of the test. So this is the chi-squared test for independence. And this is at an alpha level of 0.01. Our null hypothesis, no association between flavor preference and school level. Our alternative hypothesis is there is an association between the two. And with our conditions, it said it is a random sample of 200 students. And we need to see if all expected values are greater than or equal to 5. That gives us a large enough sample. So again, you want to go back to this, and your expected counts, how you get this, if totals are not here, you definitely want to find the totals. But for example, for Crazy Koala in high school, this is how, this is the formula for your expected counts. So it would be row total times column total, all divided by the grand total. So if I was doing Crazy Koala in high school, Crazy Koala has 90 for my row total. High school is 80, so times 80, all over the grand total of 200, which would give me 36. So this would have an expected value of 36. And again, you need to state that expected is in parentheses. And you would go and do this for each one. For Lively Lime, it would be 50 times 80 over 200. And that would be 20. For Groovy Grape, it would be 40 times 80 over 200, which is 16. And my expected value for Dull Diet Pop is 8. You do the same thing for middle school. So Crazy Cola for middle school will be 90 times 120 over 200, which is 54. And going down, you would get 30, 24, and 12. All of these are greater than or equal to 5. So you would state that all expected values greater than or equal to 5. So we have a large enough sample. And our degrees of freedom, how you find this, it is if you go back and look at your table, your rows minus 1 times your columns minus 1. So we have 4 rows, so that would be 4 minus 1. We have 2 columns, 2 minus 1. So that gives us a degrees of freedom of 3. Now we need to find our chi-squared statistic. That would be the sum of my observed minus expected, all squared, divided by expected. So with this, I would have 33 minus 36 squared for my COLA at the high school level. I'll divide by 36 plus. You don't have to write each one. You can use your dot, 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 and go to the last one, 8 minus 12, which is my Dull Diet Pop in middle school squared, all over 12 squared. And you'd get 24.6875 because your calculator will give you the statistic for you. It also will give you your p-value, and the p-value for this one was 1.79 times 10 to the negative 5. So here my p-value is less than alpha because my p-value 1.79 times 10 to the negative 5 is less than 0.01. So I reject the null hypothesis. There's enough evidence to suggest There is an association between flavor preference and school level. And let's go on to our last one. The chi-squared test of homogeneity. Is the distribution of one categorical variable the same for two or more populations? So the null hypothesis is the distribution of the variable is the same for all populations. The alternative hypothesis is the distribution of the variable is not the same for all populations. Both of those have to be within context. Your observed cell counts are based on independently chosen random samples, and the samples are greater than or equal to 2. All expected counts are greater than or equal to 5, so a large enough sample size. Degrees of freedom are the number of rows minus 1 times the number of columns minus 1. And your expected counts are the row marginal total times the column marginal total all over the grand total. The matrix will be 2 by 2 or larger, and again, the calculator will run the test for you. Let's look at our example. In the past, a number of professions were prohibited from advertising. In 1977, the U.S. Supreme Court ruled that prohibiting doctors and lawyers from advertising violated their right to free speech. The article, Should Dentists Advertise?, compared the attitudes of consumers and dentists toward the advertising of dental services. Separate random samples of 101 consumers and 124 dentists were asked to respond to the following statement. I favor the use of advertising by dentists to attract new patients. Possible responses were strongly agree, agree, neutral, disagree, and strongly disagree. The data presented in the article appears below. The authors were interested in determining whether the two groups, consumers and dentists, differed in their attitudes towards advertising. So we're going to go ahead and do this test. The process is the same. So this is a chi-squared test of homogeneity. Our null hypothesis is the distribution of consumers and dentists' opinions on advertising is the same for all populations. Our alternative hypothesis is the distribution of consumers and dentists' opinions on advertising is not the same for all populations. And observed cell counts are independent of each other, and a random sample with counts is greater than or equal to 2. All expected counts are greater than or equal to 5, so we need to go ahead and check that. So going back to our example, we would do the same thing. So for consumers and strongly agree, it would be 101 times 43 all over 225. And that would give you 19. So my expected value here would be 19. For dentists and strongly agree would be 23. 30 for consumers and agree. 37 for dentists and agree. 14 for consumers and neutral. 18 for dentists and neutral. Consumers and disagree would also be 14. Dentists and disagree would be 17. Consumers and strongly agree would be 22. And dentists and strongly agree would be 28. So looking at all my expected counts, they're all greater than or equal to 5. So we would state that after we find it. And the other thing you need to make sure that you do, which I almost forgot, is put expected in parentheses as your key so the reader knows what you're talking about. So then you would say all expected counts are greater than or equal to 5. So we have a large enough sample. Our alpha level is 0.05. Since it wasn't stated, our degrees of freedom would be 5 minus 1 times 2 minus 1, which equals 4. Make sure you show your work for that, please. Chi-squared would be sigma observe minus expected squared all over expected. That's your formula. So we would just need to show this 34 minus 19 squared all over 19 plus all the way to the last one, 46 minus 28 squared all over 28. Our calculator gives us this as 84.496. Our p-value was 1.941 times 10 to the negative 17, which really is about 0. So our p-value is less than our alpha level, because 1.941 times 10 to the negative 17 is less than 0.05. So we reject our null hypothesis. There's enough evidence to suggest the opinions of consumers and dentists about advertising differs.